All right, welcome to chapter 17. We are going to be looking at aqueous ionic equilibrium reactions in this chapter, specifically looking at buffer systems. So we'll talk about sections 1 through 3, which will talk about preparing a buffer, how to calculate the pH of a buffer, and then also what happens when an acid or base is added to a buffer. What's the new pH? So buffer solutions are solutions that resist changes in pH when an acid or base is added to the solution. The components of that buffer act by neutralizing the acid or base that is added to the buffer solution. So two different types of setups that we could have. Again, we'll start with acids and then we'll do bases on day 2 of this chapter. Significant amounts of weak acid and its conjugate base consist of a buffer, or significant amounts of weak base and its conjugate are the best examples that we can have in creating a buffer solution. So the example of a buffer system in nature is blood. Has a mixture of carbonic acid, H2CO3, which is a weak acid, and bicarbonate, HCO3-1, which is the conjugate. And so when our blood has major changes of acid or base being added, our blood acts as a buffer so that we still exist and that we're still alive. And so the pH of our blood stays typically consistent. Making an acidic buffer solution must contain amounts of a weak acid and its conjugate base. Usually the conjugate base is added as a salt. So if we think of acetic acid HC2H3O2, that is a weak acid. Its conjugate would be the salt form, sodium acetate, whereas the conjugate base is really C2H3O2-1. All right, those two need to be in the solution together. How buffers work? Well, they utilize Le Chatelier's principle. For an acidic buffer solution, we see that the addition of the base to the acidic buffer solution will create more conjugate. Well, good, because we already had conjugate in our reaction flask. And the addition of acid to the buffer system reacts with the conjugate base and it makes the original acid. Well, great. We already had the original weak acid in the solution. And so if a strong base or a strong acid is added to a buffer, the conjugate or the weak acid component, whatever reacts, remember acids and base react together. Two acids do not react together. Two bases do not react together. Whatever component is reacting will shift the equilibrium slightly and make more of the alternate. So when we're looking at buffers, the major thing to realize is that in a solution, we have HA and A- together. When you add a strong acid or a strong base to this solution, it reacts to make these two components, just a little bit more of them. And so the pH of the buffer will change slightly, but not substantially, all right? And this is because of the common ion effect. If we think about our overall acid ionization reaction, we're going to start here with this reaction and start looking at ice tables again. Now, adding salt, NaA, the sodium form of the conjugate base that is added, the weak acid shifts the position of the reaction's equilibrium to the left. All right, the added salt, specifically A- anion, is referred to the common ion. The acid plus its conjugate base are called common ions. So the addition of the common ion causes the pH to be higher than the pH of the original weak acid solution due to the lowering of the H3O+ cation. So if we think about an acid in water, this was our acid in water solution reaction up here at the top, the acid ionization reaction. To make a base, we add A-, which is a product. So Le Chatelier says shift the equilibrium to make more reactants, driving the H3O plus concentration down, which means increasing the pH. Now, this setup is how we can start to imagine what the pH of a buffer would be. It's the equilibrium between a weak acid and its conjugate base. So let's start with an ice table. Find the pH of a buffer with 0.1 molar acetic acid, HC2H3O2, and 0.1 molar sodium acetate, NaC2H3O2. And there's the Ka. That Ka will be important to note because that tells you the reaction. HC2H3O2 plus water yields H3O plus and C2H3O2 minus 1. This is the acid ionization reaction. How did I know I needed to choose this? I'm given a Ka. That's how I can determine what my overall balanced equation is. Now, the only difference from what we were talking about previously in chapter 16 is for our ice table, we have 2 starting concentrations. All right, we have 0.1 molar of acid and 0.1 molar of conjugate base. We still do not start, we will assume that we start with 0 H3O plus. Now, because there is a 0 on the product side, our change for the product will be positive, our change for the reactant will be negative, and we will go through our typical ice table. The only difference again is we have 2 starting concentrations. By looking at the Ka, 1.8 times 10 to the negative 5, we see that X should be small. We now have 2 X's that are tied to initial concentrations. And so we can cancel out both of those X's. Setting up our ice table, hydronium is X, acetate is 0.1, and acetic acid 0.1. Solve for X. X here is equal to the Ka. X is the hydronium concentration. And that's the value that we will want to find. Remember, if we want to find the pH, we need the hydronium concentration at equilibrium. So negative log of that hydronium concentration at equilibrium will equal the pH of the buffer solution. Give me 2 decimal places there for that 2 sig fig concentration. 4.74 is the pH of this buffer. All right. Only difference with buffers to start off with is we have 2 starting initial concentrations, that of the acid and its conjugate base. If X is small, we can use the assumption rule just like we had done before. If X is not small, we will have to use the quadratic equation. Now, is there an easier way to understand the pH of a buffer solution? Sure. It's the relationship derived from the Ka expression of a weak acid. And so we can use the Henderson-Hasselbalch equation. Now, this just gives us a shorthand method to calculate the pH of a buffer. The equation calculates the pH of a buffer from its pKa and the initial concentrations of weak acid and salt conjugate base, as long as X is small. So if X is not small and you are not going to use that approximation, do not use the Henderson-Hasselbalch equation. The reason why we can use the Henderson-Hasselbalch equation, it is derived from the ice table that we just did. Let's just rearrange this a little bit. Let's bring over Ka times HA divided by A minus. We're trying to isolate here the H3O plus concentration, because at the end of the day, that's what we were solving for, to find the pH. So just rearranging the Ka expression already, we can start to see how the Henderson-Hasselbalch equation was derived. Now, taking the logarithm of both sides and expanding out, we can see the Henderson-Hasselbalch equation. The pKa plus the log of HA over A minus equals the pH. Negative log, right? Negative log of both sides. This equation is extremely useful, but what we are assuming is that we will be having an X value that is small. So our Ka is very small. Now this version looks a little different from the Henderson-Hasselbalch equation that we just utilized. Negatives kind of throw a wrench in our system. So you can take the pKa plus log, notice at the numerator and denominator here, of the conjugate base over the acid equal to the pH. That's the Henderson-Hasselbalch equation that we can utilize. Again, only if the assumption rule is valid. So how do you solve for the pH of a buffer solution? Ice table will get you to that pH 100% of the time. Every single time you can use an ice table. If you want the shorthand method of the Henderson-Hasselbalch equation, go ahead and use it only if X's small approximation works. So that is where K is fairly small and the initial concentrations of acid and salt are not very dilute. So they're relatively large, right? For most problems, this means that the initial acid and salt concentration should be over 100 to 1,000 times larger than the value of the Ka. That's where we were looking at concentrations of around 0.1 and a Ka of around times 10 to the negative 4. That's a good assumption that you can use the Henderson-Hasselbalch equation. So let's use that Henderson-Hasselbalch equation. If we see our Ka here is times 10 to the negative 5, and our initial concentrations around 0.1, 0.05, that is 1,000 times bigger for the concentrations than the K. So we can use the Henderson-Hasselbalch equation. You could also do an ice table for this. That's A-OK as well. Let's go ahead and use that Henderson-Hasselbalch equation. pH is equal to pKa plus log of the base over the acid. pKa is going to be the negative log of 6.5 times 10 to the negative 5 plus log of 0.150, the concentration of sodium benzoate, divided by 0.050, the concentration of benzoic acid. For that pKa, we should be getting 4.187. And for the log of the base divided by acid, we should be getting 0.477. So the pH of this buffer is 4.66. Again, ice table would have been appropriate as well, but you don't have to do it if the X value was small. Now, the second type of calculation we can do with a buffer is determining the buffer after, or determining the pH of the buffer after adding acid or base. So when an acid or base is added to a buffer solution, the appropriate components of the buffer, whether it's the acid or the base, will counteract these additions. If you add acid, H plus, some strong acid, it's going to react with the conjugate base of the buffer, A minus, right? And it's going to make HA. On the other hand, if you add base, such as hydroxide, it will react with the acid component of the buffer, make water, which we don't often care about because it's a liquid, and conjugate base A minus. So again, we are balancing the products of those additions with the already established components of the buffer. Now, what we have to do is be able to see the change of the pH of the buffer solution. Now, the pH should remain relatively the same or maybe change slightly as long as there's significant amounts of the component weak acid and conjugate base already made in the buffer. Right? We'll talk about buffer capacity at the end of this chapter. Now, two things that we need to do. We need to first do a stoichiometric calculation to see if strong acid or strong base reacts, how much of the buffer is it reacting with? And then we'll use our equilibrium calculations again to find the new H3O plus concentration. So this is a very wordy question, but let's hang on to it. A buffer contains 0.1 moles of acetic acid and 0.1 moles of sodium acetate. There is our original buffer. It says 1 liter, just so that we understand that the stoichiometric relationship presented here for this first part of the calculation should be in moles. The value of the Ka for acetic acid is 1.8 times 10 to the negative 5. Because the initial amounts of acid and conjugate base are equal, the pH of the buffer is equal to pKa, which is 4.74. We already did that calculation earlier. All right. We want to calculate the new pH after adding 0.01 moles of solid sodium hydroxide to the buffer. Now, calculate the pH after the addition of sodium hydroxide to the solution, and we're going to ignore any small changes of the volume, all right? So when we make our ice table, again, what reaction are we starting with? That Ka tells it all. We want to use the acid ionization reaction of acetic acid with water. So for this reaction, we will be looking for our new ice table this way. But here's the question. Well, how much of our acid and conjugate base are we going to start with? Well, we have to think we're adding sodium hydroxide. So which component of the buffer is sodium hydroxide going to react with? This is a base, which means it has to react with an acid. The weak acid in the solution is acetic acid. And that reaction, notice it's not an equilibrium arrow, it's a full-on yield sign, because that strong base will go to completion and make water and sodium acetate. Now, if we start with 0.100 moles of each of these, and we add in 0.01 moles of sodium hydroxide, we will be reacting in our 1-to-1 ratio that 0.01 moles of sodium hydroxide with the acid and making an additional 0.01 moles of conjugate base. So whatever we have for our addition of strong acid or strong base, in this case, a strong base, we will be subtracting that from the component of the buffer it's reacting with, in this case, acetic acid, and adding it to the component of the buffer that it's producing, in this case, conjugate base sodium acetate. So our initial concentrations are 0.09 for the acid and 0.110 for the conjugate base. Again, we're going to assume no H3O plus to start off with. We'll do our ice table just as before. We'll look at our Ka and say, yep, that Ka is small. So we can assume the X's tied to initial concentrations are also small and solve for X. X being our hydronium concentration, which in this case, 1.5 times 10 to the negative 5 molar. The pH then, negative log of that value, 4.83. Awesome. Could you have used the Henderson-Hasselbalch equation? Absolutely, you totally could have. That is an alternative approach to this because, again, whenever you can use an ice table and do the assumption rule, you could have also done the Henderson-Hasselbalch equation. Utilizing our new concentrations after the sodium hydroxide reacted, we would be able to see that 4.74 plus log of 0.110 over 0.090. The pH, again, 4.83. Same calculation, whichever one you want to do. Buffers can also be basic, starting with a weak base and its conjugate acid as a soluble salt. Usually you see the alternative ion being the anion in this case, such as chlorine or chloride. So ammonia is a great example of a buffer with ammonium chloride. The specific components of the buffer that we would be looking at is the weak base is ammonium, the conjugate acid, ammonia, and the conjugate acid is ammonium. Notice the spectator ion of Cl-1 is not present. Again, these basic buffers, just like the basic ice tables before, we would calculate the hydroxide concentration, find the pOH, and typically we ask for the pH of a buffer. And so you would take 14 minus the pOH. Now the Henderson-Hasselbalch equation for basic buffers looks a little different because for basic buffers, we're given a KB, so we would have a pKb. So our Henderson-Hasselbalch equation would be the pOH is equal to the pKb plus the log of the conjugate acid divided by base. Buffering effectiveness and capacity versus range. The buffering range is the pH range at which the buffer can be effective. And the buffering capacity is the amount of acid or base that can actually be neutralized by the buffer. So the effectiveness of the buffer is going to depend on two main ideas. We are going to have to look at the relative amount of acid and base in the actual buffer, right? So this is acid plus conjugate base, or base plus conjugate acid. The absolute concentrations of those acids and bases overall. So not only do the concentrations need to be relatively similar to each other, but they also need to be an effective amount total. A buffer range will be most effective when 0.1 to 10 is the mole ratio, all right? So we want it to be somewhere in the same ballpark for base to acid ratio. We don't want too much acid or too much base. We want them to be almost equal so that they have the best buffering capacity and range. So substituting the Henderson-Hasselbalch equation, into the Henderson-Hasselbalch equation, we can calculate the maximum and minimum pH at which a buffer will be effective. If you take that low end, you want the base to acid ratio to be at least 0.1, then you would see that the lowest pH would be pH is equal to pKa minus 1. If you took it on the high end, its pH is equal to pKa plus 1. Therefore, an effective buffer range is dependent on the acid that you are using for your buffer, and it would be the pKa plus or minus 1. So when choosing an acid to make a buffer, choose one whose pKa is closest to the pH of the buffer you would like. A buffer will be most effective when the acid-base ratio is equal to 1, equal concentrations of acid and base. But a buffer will be effective when it is 0.1 to 10 in that range. You never want to go outside of that 1 to 10 ratio of base to acid because that is outside the effective range.